number 4. A 105 kilogram basketball player crouches down 0.400 meters while waiting to jump. After exerting a force on the floor through this 0.400 meters, his feet leave the floor and his center of gravity rises 0.950 meters above its normal standing erect position. A. Using energy considerations, calculate his velocity when he leaves the floor. Okay, so you know me. I'm not much of an artist, but we'll give this a shot. So here we got our guy, our basketball player rather. Doesn't have to be a guy. Let's say the center of gravity is here, and this basketball player is gonna crouch down. So you know me, I can't draw. Don't judge. So here we got our basketball player has crouched down. Anyway, so he crouched down 0.400 meters. So he's going to exert a force through this distance, and he's going to leave the floor. When he leaves the floor, he ends up with his center of gravity rising 0.950 meters above his normal standing position. So we're going to go 0.005. So he's now jumped. Still a very happy basketball player. And he has ended up 0.950 meters above his center of gravity where he started. Okay, now use energy considerations. Calculate his velocity when he leaves the floor. All right, so we're going to use the idea of the law of conservation of energy. The whole idea that the energy total before equals the energy total after. So we have this idea of potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Now, we're assigning this whole floor piece here as our 0 point. So, sorry. His potential energy initial is 0 because he's currently standing on the floor. We want to know his initial kinetic energy when he leaves the floor. He has a final potential energy because he's risen above a height, but he does not have a final kinetic energy because his velocity is ever so momentarily 0 at the top of his jump. So our kinetic energy initial is 1/2 mv sub I squared, and then our potential energy final would be mass times gravity times height. Now, he's 105 kilograms, so we can say 1/2 times the 105 kilograms times his velocity initial squared, which is what we're looking for, equals 105 kilograms multiplied by negative 9.81 meters per second squared multiplied by 0.950 meters. If we do the math here, we come out with an initial velocity of 4.32 meters per second. Part B then says, what average force did he exert on the floor? So part B means we need to incorporate the idea of the work energy theorem. The work done on an object equals the net change in kinetic energy. So in this case, the force times the distance equals the kinetic energy final minus the kinetic energy initial. He exerts the force on the floor for 0.400 meters. So we get force times 0.400 meters. His kinetic energy final is the energy initial is 1/2 m v sub I squared. So we get force times 0.400 meters equals 1/2 times 105 kilograms times 4.32 meters per second squared. If we solve that for a force exerted on the floor, we get a force of 2,446.4 newtons. As he's exerting this force on the floor over this distance, he must also overcome the force of his weight. So we have to include that in the total force calculation. So force equals weight equals mass times gravity equals 1,050 newtons if we use 10. So then we have to add this 1,050 newtons to the 2,446 newtons to get the total force. Part C asks, what was his power output during the acceleration phase? So in order to find power, we have to know the work done and the rate at which that work was done. So we have to use a little bit of kinematics and Newton's second law here. Net force equals mass times acceleration. The net force that he exerted was the total force to be able to rise above the floor. So 3,496 newtons equals 105 kilograms multiplied by the acceleration that occurred during the force he was exerting on the floor. So his acceleration equals 33.3 meters per second squared. We need to know the time because we need to find the power. So we now have a distance and an acceleration, and we want a time. So d equals v sub I t plus 1/2 a t squared. This v sub I being the velocity before he leaves the floor, or as he starts the force. So 0.400 meters equals 1/2 multiplied by 33.3 meters per second squared multiplied by t squared. You get a time equal to 0.155 seconds. Now we can figure out his power. Power equals work divided by time. Work equals force over a distance, still divided by time. The force is 3,496 newtons times 0.400 meters, all divided by 0.155 seconds. Oh, Boulder Dash. So power equals, sorry game, didn't have it up there for you. Power equals 9,022 watts.